the dot product. In this video, we're going to talk about the dot product, which is one way to multiply two vectors together. So I'm going to start with the generalized case, and then for the rest of the things I'm going to do, it'll be in three-dimensional space if I want to prove things. But if I can prove it in three-dimensional space, it's very easily extendable to n-dimensional space. But consider the vector A, which is the vector A1, comma A2, comma all the way out to A sub n, so an n-dimensional vector. And then B is the vector B1, comma B2, all the way out to B sub n, so the same dimensional vector. Then A dot B, that's a dot right there, A dot B is the sum, I equals 1 to n, of AI times or dot bi, meaning a1 b1 plus a2 b2 plus, and we keep going till we get to the final component, plus an bn. For example, because it's not that difficult of an idea, let a equal the vector 2, comma 3, comma 4, and let b equal the vector -1, comma 3, comma -2. Then A dot B is found by multiplying the like components, so 2 times -1, like the x's get multiplied together, then the y's get multiplied together, and the z's get multiplied together, and we add each of these products to get a final answer. So we get -2 plus 9 minus 8 equals -1. So the dot product of two vectors is not a vector, but simply a constant, or what we call a scalar. So let's look at some important properties of the dot product. This is not going to be an extensive list. I would say these are probably the most common properties, most important ones perhaps, that we encounter. So some properties of the dot product. The first property that I really want you to know is the following. Any vector dot itself is the magnitude of that vector squared. Another property is that the dot product is commutative. The order does not matter. A dot B equals B dot A. And then we'll do a distributive property as well. Again, there are many other properties that you may encounter. But A dot B plus C equals A dot B plus A dot C. And I want to get you used to some proofs. So let's prove number one. And again, I'm going to prove these things in three-dimensional space, but it's very easily extendable to n-dimensional space. But let's let A equal the vector A1, A2, A3. Then A dot A is A1, A2, A3 dot itself, A1, A2, A3. And then we multiply like terms, so the x's get multiplied together, A1 squared. And then we add and multiply the y terms together, A2 squared. Add, multiply the z terms together, plus A3 squared. Now, if we recall, the magnitude of A is the square root of A1 squared plus A2 squared plus A3 squared. And so if we square both sides, we get exactly A dot A. They are the same thing. So this one, very important. This will show up in a bunch of different places. Make sure you know that one. Let's take a look at number 3, just to give another proof. So we'll keep A as is, and then we'll add B. We'll call that B1, B2, B3. And then C, of course, will be C1, C2, C3. So let's find A dot B plus C. I'm going to start inside the parentheses. So we're going to have A dot, and then B plus C says, let's add the like components of B and C. So I get B1 plus C1, comma, B2 plus C2, comma, B3 plus C3. That's how we add vectors together. And then A dot B plus C says we're going to take A and do the dot product. So we're going to multiply like things together. So we have A1 times B1 plus C1. And then we'll do the A2, that is the Y's, times the Y's. And then we'll do the Z's times the Z's. And add each of these products together. And we'll do just a little bit more algebra. Now we can distribute, because now A1, B1, C1, etc., these are all just real numbers. So we can use real number algebra, giving us A1, B1 plus A1, C1, and then A2, B2 plus A2, C2 plus A3, B3 plus A3, C3. And then if we rearrange the order, like putting our B's together, if you would, we get A1, B1 plus A2, B2 plus A3, B3, and then putting the C parts together, so A1, C1 plus A2, C2 plus A3, C3, and notice what we have here. We have A dot B plus A dot C. And so we've shown that the dot product is distributive. So that was the proof for number 3. One final theorem and proof. And this theorem is going to become very important for us. A very, very important theorem. So here's my claim. Consider an angle theta between two vectors A and B. Then A dot B equals the magnitude of A times the magnitude of B times the cosine of the angle between them. So let's do the proof on this one. So here's our theorem. And now let's do our proof. Make this one a little bit more formal. So I'm going to start with a picture to help us out a bit. And you might not know why I'm drawing the picture. You might think, well, how did I think of doing it? Well, we'll see on the end. This is a clever way to set up the problem to help us get the proof. So I have two angles, A and B, and I'm going to put their tails together like this. And then if you recall from the video on vectors, the vector which I just drew dashed, which is actually not dashed, but just to kind of separate it, that vector is a vector A minus B. Now we're going to go back to trig and use the law of cosines. which says the following. The length of a minus b squared, so the magnitude of a minus b squared, equals the length or magnitude of a squared plus the length of b squared minus 2 times the length of a times the length of b times the cosine of the angle between them. This is the law of cosines in a triangle when we know 3 sides, like that. Or 2 adjacent sides and the angle between them. So how does this prove what we want up top? Well, let's use our properties that we learned just a little bit before, and I can rewrite some of these things. So I know that a minus b magnitude squared is a minus b dot a minus b. And then I'm going to leave the right side alone and just kind of mess with the left side just a little bit. Using our distributive property, we see that we get a dot a and then minus a dot b minus b dot a and then plus b dot b. That still equals the right side of the original. Now, a dot a is the magnitude of a all squared, right? And then a dot b and b dot a are the exact same thing. That's one of the properties we showed above. So I have minus 2, and I'll put a dot b. I'll put it in this order. And then plus b dot b is the magnitude of b squared. So now I'm going to rewrite the original right side of the equation, giving us magnitude of a squared plus magnitude of b squared minus 2 times the magnitude of a times the magnitude of b times the cosine of the angle between them. Now, magnitudes are numbers. So I have magnitude of a squared on both sides of the equation, so I can subtract them off or cancel them off. And then we have magnitude of b squared on both sides, so I can subtract them off or cancel them, leaving us with negative 2 times a dot b equals negative 2 times the magnitude of a times the magnitude of b times the cosine of theta. Now if I divide both sides by negative 2, notice that we get exactly what we want. And I'll make both these positive to kind of finish it off. We get a dot b equals the magnitude of a times the magnitude of b times the cosine of theta. So that's the end of the proof, but just a side note. Often we want to find the angle between two vectors, so we could rearrange the equation to give us cosine of theta equals a dot b over the magnitude of a times the magnitude of b. And let's do an example. Let u equal the vector 1, 4, 2, and then v will be the vector negative 3, 1, 1. And I want to find the angle between them. Like that. Well, it's pretty straightforward. The angle between the two vectors, the cosine of theta, well, we'll find the cosine of theta first, is the dot product of u and v. So I'll have 1 times negative 3 plus 4 times 1 plus 2 times 1 all over the magnitude of u. I think I said a and b. It's u dot v. So the magnitude of u, which is 1 squared plus 4 squared plus 2 squared, times the magnitude of vector v, which is negative 3 squared plus 1 squared plus 1 squared. And that's going to give us 3 over the square root of 21 times the square root of 11. Whatever that is, at this point I'm going to use a calculator, and I find that theta is the inverse cosine of that number that we have over here. And putting that in a calculator, I get approximately 78.62 degrees. Now, if you're in my Calc 1 or Calc 2 class, I often say all radians all the time, but in Calc 3 or multivariable, we often slip into 2 degrees, at least we're doing problems like this. Let me show one last example. And we want to show that the vector 2i plus 2j minus k is perpendicular to the vector 5i minus 4j plus 2k. So the cosine of theta is the dot product of the two vectors over their magnitude. So the dot product will be 2 times 5 plus 2 times negative 4 plus negative 1 times 2 all over their magnitudes. Now, I don't really need to put the magnitudes to do this problem, but I'll kind of finish it off. So I have 4 plus 4 plus 1 times the other magnitude, 25 plus 16 plus 4. But the important part is that we get the cosine of theta equals 0, which means theta equals 90 degrees, which means the two vectors are perpendicular.